The longest-lasting battery we have ever built holds its charge for a few years before it dies. The best chemical energy storage we know degrades over decades. Even nuclear materials, radioactive isotopes whose decay releases energy, run out on timescales of thousands to millions of years. Everything we have ever built to store energy eventually loses it. The universe trends relentlessly toward disorder. Energy spreads. It disperses. It degrades. This is the second law of thermodynamics, working against every civilization in the cosmos that wants to store power for the long term. But the laws of physics do not forbid long-term energy storage. They just make it extraordinarily hard. And the solutions, the physical mechanisms that could in principle store energy for millions or billions of years without significant loss, are among the most exotic structures that physics allows. Let me begin with what makes energy storage so fundamentally difficult, not from an engineering standpoint but from a physics one. Because the engineering problems are merely hard. The physics problem is deep. The second law of thermodynamics states that in any closed system, entropy, the measure of disorder, tends to increase over time. Energy does not spontaneously concentrate, it spreads. A hot object placed in a cold room cools down. A compressed spring slowly loses its tension if the material isn't perfect. A chemical battery discharges through internal self-discharge even when nothing is connected. A charged capacitor leaks. Everything we know about storing energy is a temporary, imperfect resistance against this universal tendency. The reason entropy wins in the long run is statistical. There are vastly more ways for energy to be spread out than concentrated. A gas of molecules is vastly more likely to distribute itself evenly through a container than to spontaneously concentrate in one corner. The probability of spontaneous concentration is not zero, it is just so astronomically small that it never happens on any humanly relevant timescale. Entropy is not a law of nature in the same sense as conservation of energy. It is a statistical near-certainty so overwhelming that it functions as a law. For a civilization trying to store energy for millions of years, the enemy is not just entropy in the abstract, it is every specific mechanism by which stored energy leaks, degrades, or disperses. Thermal radiation, quantum tunneling, cosmic ray interactions, gravitational perturbations, nuclear decay, vacuum fluctuations, and more. The longer the storage timescale required, the more exotic and obscure the leakage mechanisms become, but they never go to zero. So what does work? What mechanisms could in principle store energy stably for geological or cosmic timescales? The first and most straightforward mechanism is gravitational potential energy. Gravity is a conservative force. It stores energy without dissipation in a perfect system. A mass raised to a height stores gravitational potential energy equal to the mass times the gravitational acceleration times the height. When released, that energy can be recovered. Civilizations have used gravitational storage since ancient times. Water reservoirs behind dams store energy as potential energy, released when water flows downhill through turbines. The storage is efficient, the release is controllable, and the energy does not leak unless the water evaporates or the reservoir is disturbed. On a cosmic scale, gravitational potential energy is stored in orbital configurations. A moon orbiting a planet orbiting a star orbiting a galactic center, all are storing energy in their orbital motion. The energy is real and recoverable. Tidal interactions between orbiting bodies convert orbital kinetic energy to heat over billions of years. The moon is slowly spiraling away from Earth as Earth's rotation slows due to tidal friction, the energy leaking as heat in the oceans. But for a carefully managed, non-dissipative orbital system in a near-vacuum environment, gravitational storage can persist for billions of years. An advanced civilization might store energy in the orbital configuration of carefully placed masses, asteroids, small moons, engineered objects, whose gravitational interactions store enormous quantities of potential energy that can be released on demand by adjusting the orbital parameters. This is gravitational energy storage at a civilizational scale. The storage medium is space-time geometry itself. The losses are minimal over very long timescales if the system is maintained in vacuum and protected from perturbations. The second mechanism is rotational kinetic energy. A rotating mass stores kinetic energy equal to half its moment of inertia times the square of its angular velocity. Flywheels are the simplest example. A spinning wheel stores energy and releases it as the wheel decelerates. Modern composite flywheels, spinning in vacuum on magnetic bearings, can store energy with very high efficiency and very low self-discharge. Perhaps a few percent per hour in the best current designs. Scaling this up, a civilization might spin massive objects, asteroids, engineered spheres in perfect vacuum with electromagnetic bearings that produce no friction. The storage medium is kinetic energy in the rotation. The losses come from electromagnetic radiation from the rotating charge components, from quantum effects that are negligible at macroscopic scales, and from occasional gravitational disturbances. For a perfectly constructed superconducting magnetic bearing in a deep vacuum away from gravitational gradients, the leakage rate could be extraordinarily small, but there is a fundamental limit on how much energy a rotating object can store. As a rigid body spins faster, the centrifugal forces increase. At some angular velocity, the material's tensile strength is exceeded and the object flies apart. The maximum rotational energy density is determined by the specific strength of the material, the ratio of tensile strength to density. For ordinary metals and composites, this limit is modest, but for degenerate matter, the exotic, extremely dense matter found in white dwarfs and neutron stars, the specific strength is orders of magnitude higher. A cylinder of neutron star material, rotating near its breakup velocity, could store energy densities that dwarf anything achievable with ordinary matter. An advanced civilization with access to neutron star material could, in principle, build rotational energy storage systems of extraordinary capacity and longevity. The third mechanism involves magnetic energy storage. A current flowing through a superconducting coil stores energy in the magnetic field indefinitely. A true superconductor has zero electrical resistance and experiences no ohmic losses. The energy stored in the magnetic field persists as long as the current continues to flow, which in a perfect superconducting loop can be forever without any external power input. Superconducting magnetic energy storage, SMES in engineering terminology, already exists in small-scale human technology. The challenge is maintaining superconductivity at accessible temperatures and scaling the storage capacity to civilizational needs. For an advanced civilization, this becomes far more tractable. High-temperature superconductors, materials that superconduct at significantly elevated temperatures, are an active area of research. A civilization with millions of years of materials science might have discovered room temperature or high-temperature superconductors that can be manufactured in bulk. With such materials, enormous superconducting loops, perhaps wound around entire asteroids or built into orbital rings, could store the magnetic energy of enormous persistent currents indefinitely with zero resistive loss. The only leakage mechanisms for a perfect superconductor and a perfect magnetic storage system would be quantum mechanical tunneling processes that allow tiny amounts of current to cross junctions, or vortex dynamics in the superconductor that cause slow flux creep. These are extraordinarily slow processes on geological timescales. A sufficiently engineered superconducting energy storage system could in principle retain its stored energy for millions of years, with losses measured in fractions of a percent. The fourth mechanism is matter-antimatter storage. We discussed antimatter as a propellant in another context, but antimatter is also a perfect energy storage medium. The energy density of antimatter in terms of energy per unit mass is higher than any other known storage medium. 1 kilogram of antimatter, stored perfectly and annihilated with 1 kilogram of matter, releases 180 terajoules. This is the theoretical maximum E equals mc squared applied to the full mass of both particles. The storage challenge is severe, as we discussed. Antimatter must be isolated from all ordinary matter, which requires perfect magnetic or electromagnetic confinement. But for an advanced civilization, the physics of penning traps and electromagnetic confinement scaled to much larger sizes is well understood. A civilization that can produce antimatter in bulk can also design confinement systems of far greater scale and sophistication than anything we currently operate. Antimatter does not decay. A positron does not spontaneously turn into something else over time. A perfectly isolated antiproton is stable forever. The only leakage mechanism is the failure of the confinement. If the confining fields weaken and the antimatter touches the container walls, annihilation occurs. But a civilization maintaining its confinement infrastructure actively would face no intrinsic loss from the storage medium itself. The fifth mechanism is one that pushes into more speculative but genuinely exciting territory: the use of black holes as energy storage systems. A black hole stores mass energy with perfect efficiency. Anything that falls into a black hole adds its mass energy to the black hole's total mass. That energy is preserved. The black hole's mass increases by exactly the amount of energy added, divided by c squared. Nothing is lost. The energy is stored in the curved geometry of space-time surrounding the black hole. Can you get it back? This is the key question. And the answer, as we discussed in the context of black holes as energy sources, is yes, through the Penrose process or the Blandford's-Nyack mechanism for rotating black holes, and through Hawking radiation for all black holes. But there is a subtlety for energy storage specifically. If you drop matter into a black hole for storage and then try to extract it via Hawking radiation, you face an efficiency problem. Hawking radiation extracts energy as thermal radiation at a specific temperature, higher for smaller black holes, lower for larger ones. For a stellar mass black hole, the Hawking temperature is so low, fractions of a nanokelvin, that the radiation is swamped by the cosmic microwave background radiation, which is about 2.7 Kelvin. You cannot extract useful work from a thermal reservoir colder than its environment. For Hawking radiation to be a practical energy extraction mechanism, the black hole must be small enough to have a Hawking temperature higher than its surroundings. As the universe cools, as the cosmic microwave background redshifts to lower and lower temperatures over trillions of years, even small black holes will eventually be warmer than their environment and will radiate usefully. This is a genuinely remarkable physical fact. In the far future of the universe, after all the stars have died, after all ordinary matter has decayed or been consumed, after the universe has cooled to near absolute zero, the only remaining energy sources will be black holes of various masses, radiating away their stored energy through Hawking radiation. The timescale for a stellar mass black hole to fully evaporate is roughly 10 to the power of 74 years. For a supermassive black hole of 1 billion solar masses, the timescale is closer to 10 to the power of 100 years. A civilization that could survive long enough to operate in this era, an almost incomprehensibly advanced and durable intelligence, would find black holes to be the only remaining energy source in the universe, and that energy would be available, slowly but persistently, for timescales that make the current age of the universe look like a brief moment. The use of black holes as energy storage banks, depositing matter and energy for extraction later via Hawking radiation or rotational energy extraction, represents the ultimate form of long-term energy storage that the laws of physics allow. It is not a near-term technology. It requires engineering at scales we cannot currently imagine, but it requires no new physics. Every mechanism involved is described by equations we have tested and confirmed. The sixth mechanism I want to discuss is one that is more speculative but appears in serious theoretical discussions. It involves the energy stored in the vacuum, in the quantum ground state of empty space itself. Quantum mechanics tells us that empty space is not truly empty. Virtual particles pop in and out of existence continuously, and the quantum fields that pervade all of space have a ground state energy, a zero-point energy that is Tun-Goa. The universe is suffused with this vacuum energy, also called zero-point energy, the cosmological constant. The term in Einstein's equations that drives the accelerating expansion of the universe may be related to this vacuum energy. If the vacuum energy density is what drives cosmic expansion, it has an enormous energy content spread across the observable universe. In principle, the energy of the vacuum is inexhaustible. It is a property of space itself, not a finite resource being depleted. Could a civilization tap vacuum energy? This is highly speculative. There is currently no known mechanism for extracting net energy from the quantum vacuum in a way that does not violate conservation of energy. The Casimir effect, which results from differences in vacuum energy between constrained geometries, produces forces but not net extractable energy. The energy you expend bringing the plates together equals the energy you extract from the Casimir force. Attempts to build Casimir effect engines are not prohibited by quantum mechanics, but are prevented by the thermodynamics of the process. Whether future physics, particularly a complete theory of quantum gravity, reveals mechanisms for practical vacuum energy extraction is an open question. It is one of those genuinely uncertain frontiers where honest physicists say, we do not know enough to rule it out or confirm it, but vacuum energy is real. Whether it is accessible as a practical energy source for a civilization remains unknown. Let me now connect all of this back to the broader question of civilization longevity and what it tells us about what might be out there. A civilization that has solved long-term energy storage is a civilization that has escaped one of the most fundamental constraints on survival. Every civilization that depends on a living star for energy is vulnerable to stellar evolution. Stars change. They brighten as they age. Our sun is about 30% brighter now than when life first appeared on Earth, and will become uninhabitable for complex life within 1 billion years or so, as it gradually heats the Earth beyond the range that supports biology. A civilization still dependent on unmediated stellar radiation when this happens faces a severe survival challenge. A civilization that has developed independent energy storage, that has banked sufficient energy in gravitational, magnetic, antimatter, or rotational form to operate independently of its star for geological timescales, is no longer subject to this threat. It can survive stellar evolution, stellar death, even the eventual heat death of the stellar neighborhood. It becomes, in a meaningful physical sense, much more durable than any star-dependent civilization. The Kardashev scale measures civilizations by their energy consumption. Type 1 uses the energy of an entire planet. Type 2 uses the energy of an entire star. Type 3 uses the energy of an entire galaxy. But a perhaps more meaningful measure is not energy consumption, but energy resilience. How long a civilization can maintain its operations without access to an active energy source. A civilization with robust long-term energy storage, regardless of its consumption rate, is fundamentally more survivable than one entirely dependent on continuous production. And survival over millions of years is what separates the civilizations we might detect from the ones we never will. A civilization that builds, flourishes, and collapses in a few thousand years, however brilliant, leaves little time for contact with other civilizations, given the communication delays imposed by the speed of light. A civilization that survives for millions or billions of years has time, perhaps enormous amounts of time, to expand its footprint, refine its signals, and perhaps eventually make its presence known to any civilization patient enough and sensitive enough to look. Long-term energy storage is not just a technological problem, it is a civilizational survival problem. And the solutions, gravity, rotation, superconducting magnetism, antimatter, black holes, are not science fiction, they are physics. Real, tested, equation-backed physics that any intelligence in any corner of the universe is subject to and could, with sufficient time and development, exploit. The energy is there. The universe stores it in extreme forms all around us, in the spin of black holes, in the orbits of moons, in the persistent currents of neutron star matter, in the perfect confinement of antimatter traps, in the long, slow decay of enormous masses toward thermal equilibrium. Any civilization that learns to read these storage mechanisms, to exploit them, to fill them, and draw from them on the timescales the universe offers, that civilization outlasts its star. It outlasts its galaxy's active phase. It may, in some form, outlast almost everything. That is what the physics permits. And physics, as always, does not play favorites. It offers the same opportunities to every intelligence that arises anywhere in the universe. The question is only who has been around long enough to find them.